Hello everyone. Welcome to the next lecture on the complex analysis. Today I will explain you the exponential function as one of the elementary function. Myself Dr. Harish Garg. You can follow and subscribe my YouTube channel. Now in this lecture we will learn the basic concepts of the elementary functions of the complex variable. There are the different kind of the elementary functions and few of them are exponentials, logarithms, sine and cosine and so on. In this lecture, I will explain you the idea of the exponential part. Later on, I will explain you the logarithm functions followed by the trigonometry part. Now, first of all, I will explain you the concept of the exponential function. What is the definition of the exponential function? Exponential function is denoted by exp of the complex variable z, or sometime it is denoted by e of z. And this function is defined as exponential of z is equal to exponential of x plus iota y, or sometimes you can say e raised to power z is e raised to power x plus iota y. I can also write this function is e raised to power x, e raised to power iota y. Now for this part I can apply the Euler's formula. Then you can write this function is e raised to power x cos of y plus iota sine of y. Make sure students your z, which is defined as x plus iota y, is a complex number where x and y are my real. Fine. For any two real number, we can define the complex number by defining x plus iota y. For more detail about the complex variables and the complex function, you can watch the playlist complex analysis, and in this playlist you can see the various lectures start from the complex numbers, complex conjugates, Cauchy-Riemann equations, Cauchy integral formula, residue, all are available in the single playlist. You can follow and subscribe the YouTube channel. Now, whenever you have defined the exponential function, the first things come in our mind is check whether the function is entire or not, or whether the function is analytic or not. How you can check about the entire function, or how you can check about the analyticity? We have to check the Cauchy-Riemann equation. Fine. How you can check the Cauchy-Riemann equation? If I consider the function f of z, which is defined as u plus iota v, then what is the Cauchy-Riemann equation suggested you? The Cauchy-Riemann equation suggested you can calculate the u partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, partial derivative of v with respect to y. And whenever these two equations are satisfied, then CR equations satisfied. And whenever the partial derivatives are my continuous, then you can say the function is my analytic. Clear? Now if you compare them, what is my u? U is a real component, e of x cos y, v is my e of x sin y. Now can you calculate the partial derivative of u with respect to x? Partial derivative of u with respect to x is e raised to power x cos y. Partial derivative of u with respect to y is minus e raised to power x sine of y. Similarly, partial derivative of v with respect to x is e raised to power x sine y. Partial derivative of v with respect to y is e raised to power x cos y. Now clearly say del u by del x is equal to del v by del y, and they are same with the opposite sign. Therefore, CR equations satisfied. Fine. Also, you can see the partial derivatives that you have obtained are my continuous. Why? Because exponential and the trigonometry functions are always continuous. Therefore, my given function is, now once the function is entire, we can calculate the derivatives. Fine. How you can calculate the derivative? You can take partial derivative of u with respect to x plus iota partial derivative of v with respect to x. Fine. Now you can substitute the value partial derivative of u with respect to x and partial derivative of v with respect to x. So if I substitute them, e raised to power x cos y plus iota e raised to power x sin y. I can take e raised to power x is common, which is defined as cos y plus iota sin y. Again, you can see by using the Euler formula, which is defined as e raised to power iota y, that is e raised to power z. That means if you take the exponential functions, derivative is again the exponential function. And you can see the same property is hold whenever you have the real exponential function. Whenever you have taken e of x, x is my real, then what is the property is derivative of the exponential function is exponential and e of x is differentiable everywhere. Fine. The same property hold whenever e raised to power z. Because e raised to power z is analytic, so it is differentiable everywhere, and the derivative is also e raised to power z. So that is the first similarity. That is the first similarity between the e raised to power x and e raised to power z. We will see in this lecture what is the basic difference between e raised to power x and e raised to power z. Fine. The first similarity between the e raised to power x and e raised to power z is both are differentiable everywhere and the derivative is my set. Now based on this, we can define the first property, because we all know exponential e of x1, e of x2, whenever x1 and x2 are my real, then we can define the function is x1 plus x2. So can we say the same property hold for the complex number also? The answer is yes. How you can prove that? It's a very simple. We can start with the function f of z is e raised to power z, e raised to power c minus z, where c is my any complex number. Fine. I can take the two part. Now you can define the derivatives. So I can use the product rule, that is e exponential of z into exponential of c minus z plus exponential of z and exponential of c minus z, and the derivative of c minus z is minus 1. So that will be, you can see that will be cancelled out. The first derivative is my 0. What does the meaning of that? If the derivative is 0, that means the function is constant. And when it will be constant, according to this case, you can see the function is constant is e raised to power c. Fine. Or you can see e raised to power c will be occurring whenever f of 0. So that means f of z is my exponential of c. I can substitute the f of z in equation number 1. You will get the expression is exponential of c is exponential of z into exponential of c minus z. Now, because c is my any complex number, I can take c is my z1 plus z2, and I can take z is my z1. If I substitute the given expression, it will be exponential of z1 plus z2, which is equal to exponential of z1 into exponential of z2. And this is the required proof of the first property. Second property is, or you can say that this property is known as the addition theorem of exponential. Second property is, we all know in the real component, whenever x is my r, e raised to power x can never be 0. Fine. The same property hold for the complex number as well. How you can prove that? By using the definition, I can return this number is e raised to power x cos y plus iota sin y. Fine. And we all know x is my real, y is my real. Fine. So if x is real, exponential part can never be 0. Moreover, cos of y and sine of y both can never be 0 at the same time. Both can never be 0 at the same time. Why? Yes, anybody tell me? Why it can never be 0 at the same time? Because we all know sine square y plus cos square y is equal to 1. Fine. So that's why both can never be 0 at the same time. Therefore, exponential part is my non-zero. One of them is my non-zero. So the product is my non-zero. Clear? But we all know exponential of x is always be greater than 0 whenever x is my real. But you can see we have proved that exponential of z is my non-zero. That means exponential of z may be less than 0 or exponential of z is greater than 0 as well. Fine. So we have proved that exponential of z can be negative. But for the real case, it is always positive. How you can prove that exponential of z is less than 0? I can choose z is my pi iota. Then what is the value of the e raised to power z? E raised to power pi iota. I can define by the Euler theorem is cos pi plus iota sine pi. Sine pi will be 0. Cos pi will be my minus 1. And you can say this number is my less than 0. Fine. So what is the first basic difference? I can write here. What is the first basic difference between e raised to power x and e raised to power y? The first basic difference is e raised to power x is always greater than 0, while e raised to power z can be less than 0 or it can be greater than 0. The second basic difference between them is e raised to power x, we all know it's a non-periodic functions, but e raised to power z is my periodic functions. And once we know it's a periodic, then the question arises is what is the meaning of the period or what is the period of the exponential part. So for that case, we will firstly define you the concept of the period. Clear? Now, what is the meaning of the period is? As we know, if I consider, let p be the period of the function f of z. By the definition of the periodic, that means z plus p, which is equal to f of z. Make sure, students, because we are talking about the complex function, the p is also the part of the complex part. Clear? Now, once we know f of z plus p, so that means p is the period of the complex function. So can you calculate the value of the z of 2p? I can define this number is z plus p. Again, by using the definition 1 or equation 1, I can write as a z plus p. Fine. Again, by using the equation 1, I can write as the f of z. So what does it implies? 2p is also the period of f of z. Similarly, you can prove that 3p is also the period of fz. 4p is also the period of the fz and so on. Clear? So if I define the period p is the period, then 2p, 3p, 4p all are my periods. But out of these periods, 2p, 3p, 4p and so on, which one is the smallest one? Which one is the smallest period? The smallest period is known as fundamental period or called as the primitive period. Clear? Now for the exponential part, how you can calculate the periods? I will tell you the two different methods. The first method I can use by the definition. Fine. So how you can prove that? I can assume let p is the period of the f of z. That means f of z plus p is f of z. I can substitute the value. It is e raised to power z plus p is equal to e raised to power z. Fine. So I can take p is my period. So I can choose alpha plus iota beta is a part of the complex variable or the complex number where alpha and beta are my real. So I can choose, because this is for all z. So for the sake of convenience, I can choose z is 0 and p is my alpha plus iota beta. So I can substitute e raised to power iota alpha into iota beta is my 1, e raised to power 0 1, or I can write as e raised to power alpha cos of beta plus iota sine of beta. Fine. Now you can compare, you can equate the real and the imaginary part. Real part is e raised to power alpha, cos beta is my 1, e raised to power alpha, sine of beta is my 0. Fine. Because alpha and beta are my non-zero. Sorry. Alpha and beta are my real numbers. So that implies e raised to power alpha can never be 0. And e raised to power alpha is always positive. Clear? So that means because e raised to power alpha can never be 0, that implies sine of beta will be 0, which implies beta is my n pi. Or instead of the n pi, I can write it as a 2n pi. Fine. Why I can write it as a 2n pi? I will tell you. Fine, where n is my any integer. I can substitute in the given first equation. That will be cos 2n pi. It will be 1. And we all know cos of 2n pi iota is always plus 1. That implies e raised to power alpha is my 1. This implies alpha must be 0. Fine. Otherwise क्या होगा? If you choose beta is my n pi, then you can substitute in the given e raised to power alpha, cos of n pi is my 1. Fine. What is the e cos of n pi? It will be 1. Fine. Then you have to choose e of alpha as minus 1 raised to power n. But e raised to power alpha can never be less than 0. Fine, because alpha is my real. So when it will be positive? Whenever n is my even number. So whenever n is my even, that means this n is basically my 2n. So that's why I write directly here is 2n. Clear? So therefore, you can see alpha is 0. So what is the p? Alpha plus iota beta. Alpha is my 0. Beta is my 2n pi. Therefore, the period is 2n pi iota. Once we can define the period is 2n pi iota, that means 4n pi iota is also the period, 6n pi iota is also the period, and so on. But the smallest period is 2n pi iota is my fundamental period. But make sure students, whenever the period is my complex number, then you can define the primitive or called as the fundamental period only for those cases whose imaginary part is my positive. Fine. Like in this case, what is the imaginary component? Imaginary part is 2n pi, which is always greater than 0. Fine. So the period is, you can see the period is 2n pi iota, 4n pi iota, 6n pi iota, and so on. What is the fundamental period? Look at all those numbers whose imaginary part is positive. These blue lines, and the number, this one is my smallest part. However, if I say my period is say minus n pi iota, for example, then where n is my integers, it may be positive, it may be negative. So minus of 3 pi iota is a period, minus of 2 pi iota is a period, minus pi iota is a period, plus pi iota is a period, 2 pi iota is a period, and so on. Now can you find the fundamental period? Now by the definition is, look at the fundamental period whose imaginary part is greater than 0. So what is the imaginary part is? Minus n pi. So these underlined red colors are my imaginary parts. Now look at that which is greater than 0. Only these components. Now look at the smallest value is pi iota is my fundamental period of this function here. Clear? Chaliye. Next one is, and this is again similar. Why? Because if we assume f of z is, I can start with e raised to power z plus 2n pi iota. I can substitute z is x plus iota y. I can open them. You can see it is cos of y plus 2 pi sine of y plus 2 pi. This number will be cos of y, this number will be sine of y. तो ये किसके इक्वल बन जाएगा? That is e raised to power iota y. Again, you can see the function e of z has a periodic function with a period 2n pi iota. So once we can say the function is periodic, that means exponential of z1 is equal to exponential of z2 if and only if z1 is equal to z2 plus 2n pi iota. That's the meaning of this case. Fine. Or in other words, what can you say? If I choose f of z is exponential of the z, then f of z1 is equal to f of z2, which implies z1 is not equal to z2. Why? Because you can see they are not equal. They are the addition of the 2k pi. What does it means? F is not 1 1. That means exponential function of the z is not 1 1. However, we all know exponential of the real part is always 1 1, but exponential of z is not 1 1. Exponential of the real is not a periodic, but exponential of the imaginary part, exponential of the complex part is always periodic. Exponential of the x can never be less than 0. However, exponential of the complex part can be less than 0. That means these are the basic difference between the e raised to power x and e raised to power z. And you can see e raised to power x is not a periodic, but it is a periodic. Exponential can never be negative, but it can be negative. Exponential of real is always 1 1, but it is not 1 1. That is the basic difference between them. But if somebody will ask you what is the similarity, between the e raised to power x and e raised to power z? E raised to power x is differentiable everywhere. Fine. E raised to power z is differentiable everywhere. First derivative of the real exponential is same. The derivative of the complex number is also same. Fine. Another is exponential part will satisfied by this additive or addition theorem. The same for the complex number as well. Now I will explain you with the help of some numerical example. Remember students, you have to target to solve. Your target is to find the value of the z. Fine. How you can find the value of z? Your target is to find the value of x plus iota y. That means your basic target is to find the value of x and y. Clear? I will tell you a very simple approach. First of all, you can draw it graphically. Where is the 1 plus iota lies? This is the value of the x. This is the value of the y. 1 plus iota lies in the first quadrant. Fine. So 1 plus iota lies in the first quadrant. Now whenever you will see the complex number on the right hand side, you can write in the polar form. R e raised to power 2n pi is my period plus theta. Fine. That means you can write in the polar form. How you can write any of the complex number z in the polar form is, we can use the idea of modulus and argument. For more details, you can watch the lecture of modulus and argument under my playlist. I will tell you the simple recall. If your complex number is x, z is equal to x plus iota y, I can write z is r e raised to power 2n pi plus theta. Then what is the value of the r? R you can write as x square plus y square, and theta will be tan inverse y over x. Fine. Now can you calculate the value of r? If you compare the number x, z is x plus iota y, x is my 1, y is my 1. the number will be root 2. Can you find the angle? That is a tan inverse y over x. Tan inverse 1 is pi over 4. Clear? I can substitute the value in the given expression. 1 plus iota is root 2 e raised to power iota 2n pi plus pi over 4. I can substitute this equation value in the equation number 1. E raised to power 2z minus 1, which is equal to root 2 of here. Now you can substitute the value of the z also. Z is my x plus iota y. E raised to power 2x minus 1, that's a real. E raised to power iota y. Fine. Now you can compare the coefficients. That is my real component. You can see the real component is 2x minus 1 is root 2. And if you compare them, 2 of y is pi over 4 plus 2 and pi. Can you find the value of the x? 2x minus 1 is log of root 2. And can you find the value of the y? Is pi over 8 plus n pi. So can you find the value of the x? It is 1 by 2, 1 plus log of root 2, and y is my same number. Clear? Now once you can find the value of the x and y, you can substitute in the required solution. That is x plus iota y is the correct answer of the problem. Look at the second one. Again, the right hand side I can written as minus 2 plus iota 0. So where it lies minus 2 comma 0? In the border of the second and third. Clear? So can you find the value of r? R will be minus of 2 square plus 0 square, that will be 2. Theta will be tan inverse y over x, that is a tan inverse 0. But remember students, we need minus of 2 lies in the second and the third quadrant. That means, but the 0 lies in the first quadrant. How you can write? Lies between pi by 2 and pi. So that will be pi. Tan of pi will be 0. So your r is 2, theta is my pi. I can substitute in the equation. So therefore, e raised to power z will be twice e raised to power iota 2n plus 1 pi. I can substitute the value of the z, x plus iota y. Compare the coefficient. E raised to power x is my 2, y will be pi plus 2n pi. X will be my log of 2 and y will be 2n plus 1 into pi. Therefore, your solution is x plus iota y. I can substitute the value of the x. I can substitute the value of y is the required answer of the problem. Look at the next one. Again, minus 1 plus iota. I can return this number is iota 2 and pi plus theta. Where it lies? X is my minus 1, y is equal to 1. It lies in the second quadrant. So we can say what is the r? Minus 1 square plus 1 square, that will be root of 2. Theta will be tan inverse minus, that is a y over minus x. It is my minus pi by 4. But where is a minus pi by 4? Minus pi by 4 lies in the fourth quadrant. Fine. But we need a second quadrant, that is between the pi by 2 and pi. So I can write it is pi minus pi by 4. Fine. Instead of the minus pi by 4, I can write it pi minus pi by 4. That will be 3 pi by 4. Now you have the theta. 3 pi by 4 I can substitute here. So therefore, from the equation number 1, I can write is 5 root 2 e raised to power. Now you can compare the coefficient. X will be 5 root 2, y will be 3 pi by 4 plus 2n pi. You have the value of x. You have, sorry, e raised to power x. So what is the x is? Log of 5 root 2 and y is my same. Therefore, the z will be x plus iota y is the required answer of the problem. As I mentioned you can follow this playlist, watch the various lectures related to the Cauchy-Riemann equations, harmonic functions, Cauchy integral formula, and many more lectures. The complete complex analysis playlist available for you. I will come up with the next lecture on the elementary function sine and cosine part. Till then, you can like and comment on this video. You can share this video with your friends. Happy learning always. Thanks for the watchings and thanks for the support. Best wishes, students, always. Happy learning.